In previous videos, we have focused on the design of a grid-connected PV system. In this section, you will learn how to carry out a detailed design of a standalone PV system or off-grid system. In particular, in this video, we will discuss the loss of load probability, which is an important concept for standalone PV system design. Choosing a good design is even more critical for standalone systems than for grid-connected systems. This is because a standalone PV system does not have the electricity grid as a backup. For an off-grid PV system, the backup is provided by the storage components, which store energy in times when the PV modules generate more electricity than the loads consume, and it can deliver energy to electric appliances when the load demands exceeds the generation. The storage component, which is usually a battery bank, is a crucial system component that directly influences the reliability of the PV system. Properly sizing the battery bank is therefore one of the most important design steps in a standalone PV system. A critical parameter for sizing the battery bank is the number of autonomous days. This is the number of days that the PV system should be able to power the loads without energy generation. The appropriate number of autonomous days depends on a number of factors. For larger PV systems, such as in a remote building or in telecommunication systems where the load demands are high, the number of autonomous days can be determined based on their location. The selection can be made using the following table as a guideline. Here, the number of autonomous days for a certain location are given based on their latitude. You can see that the higher the latitudes, the larger the number of autonomous days. This is an obvious correlation, as you know that the daily radiance decreases as you move further away from the equator. Since the latitude is 0 at the equator, the number of autonomous days increases with increasing latitude. For standalone PV systems with small load demands, a fully autonomous system can be more easily achieved. Here we see a simple example of a standalone PV system. This is an infotainment spot that is fully powered by solar energy with a battery backup. The load is a simple tablet that requires only a few watts of power to operate. For any location in Netherlands, this system is fully autonomous at all times with just a single battery as a backup. One of the crucial concerns during PV system design is reliability. The reliability of a grid-connected PV system will always be 100% as long as the electricity grid is stable. However, a standalone PV system is only reliable until the batteries run out. Sizing the battery bank is therefore a crucial step in the design of standalone PV systems. To quantify the PV system reliability, we use the loss of load probability, or LLP. Let's first introduce some concepts related to the LLP. The first parameter is the E-fail. E-fail is defined as the energy required by the electric load that cannot be delivered by the PV system. This occurs, for example, if there is no energy generation for a period longer than a number of autonomous days. The second parameter is the E-dump. E-dump is defined as the energy produced by the PV array that is neither used to power a load nor stored in the batteries. This can occur, for example, if the PV generation is greater than the load consumption and the batteries are already full after a number of sunny days. It therefore basically represents the overproduction of the PV array in your PV system. Finally, the LLP is defined as the ratio of the energy that the PV system fails to deliver to the loads to the total energy requirement of the loads. It is a way to check the level of autonomy of the standalone PV system. Note that to have a very stable PV system, the loss of load probability should be as low as possible. To avoid unnecessary investment costs, E-dump should also be kept as low as possible. The recommended LLP value depends on the loads in your PV system. This table provides typical values of recommended LLPs for different applications. For illumination, the typical recommended LLP is 10 to the power of -2. For appliances, it is 10 to the power of -1, and for telecommunication, it is 10 to the power of -4. you can notice that telecommunication system has a very low LLP, where it is allowed to miss only 1 watt out of every 10,000 watts. To conclude, in this video we discussed the loss of load probability as a performance indicator of a standalone PV system. You will see in a later video that the design evaluation of a standalone PV system is based on achieving appropriate LLP values for a particular application. The design will only be approved if the LLP levels of a PV system design are sufficient. In the next video, we shall begin modeling the standalone PV system.